Okay, good morning. It's Thursday, last day, also for me. I'm MaurizioGazzola. I am responsible for optical architecture in Cisco. And this session is fall in the security portion of, in terms of topic, even if is a little bit deeper on the technical aspect of what means the quantum safe approach for optical network. First of all, the goal of this session will be understanding what are the security threats that the quantum computer can provide, if the threats are real, what are the possible solutions, and what is the Cisco strategy. So that will be the goal of this session, but this session is selected as a grade 3 in terms of technical because we will go a little bit deep on what is the quantum security. First of all, let's start from the basic. The security threat is associated to a quantum computer. Nice. The quantum computer, I don't know if you read all the announcements that are provided on the news. The quantum computer could have multiple applications, can completely revolutionize the drug design, can provide logistic optimization, can provide much better weather forecasting, much better finance forecasting. Of course, can provide a major impact on AI and machine learning, and it's mainly the fact that you can see here, I can, with the Moore law, I can double, the transistor every 2 years, etc., but I have a linear growth. Sorry, in order to satisfy the requirement, I needed to have an exponential capacity on the quantum, and why the Moore law that define the pace of the silicon is as linear, every 2 years I double. The quantum computer can provide exponential capacity in terms of computing power, but without this exponential requirement in terms of resources. How is this possible? It's mainly the fact that the classic computer is based on 0 and 1. The classic bit, working serial approach, can be as fast as you imagine. You can imagine all the GPUs of NVIDIA. They are very, very fast, but they are still 0, 1, 0, 1, treated in a serial way. The quantum computer is completely different. The quantum computer relies on a different concept that is the qubit. The qubit is not a 1 or 0. The qubit is a probabilistic approach to something that can be 0, 1, and all the state between 0 and 1. That is a completely mindset change, because you say that I have a 0 and 1. What means 0? All the probabilistic state between 0 and 1. The fact that the qubit is not just an example of the electronic. You have a transistor in 2 states, 0, 1. That is how the computers are built. The quantum computer, besides that there are many, many different ways to make a quantum computer, the minor entity is in a state that is undefined. Leveraging on the quantum mechanic physics, those entities are in state that if you are not measuring it, you don't know if they are 0 and 1. They are in a probabilistic state between 0 and 1. And that is the principle on which the quantum computer is built. But what does it mean? Just to give an example. You can imagine that you have a stream of bits, 0, 1, 0, 0, so you have 10 bits. That is what I can build. If I have 100 bits, I can build something with 100 coefficients. The qubit, no. The qubit leverages on what is called the superposition. The superposition is this concept that it is a combination of all the possibilities of 0 and 1. So with the 2 qubit, give me a superposition of 4, 3 qubits is a superposition of 8, 2 exponential 3, n qubit is a superposition of 2 of n possibility states. And so intuitively, because behind that there are tons and tons of math, intuitively say that, okay, I have something that with 100 qubits give me 127, 10 exponential 30th in terms of capability of possibility to compute versus the bit. So you can imagine this is why a problem of a sequential problem, a classical computer need 400 years to solve it. A quantum computer, the same problem can be solved in 1 second. Again, this is the theory, the concept, but this is why there is so much hope, and by the way, billions and billions of dollars of investment on the quantum computer. Before moving ahead, let me make a step back on the cryptography. When we speak about cryptography and quantum threat, we are thinking to 3 points. So there are what is called the symmetric key cipher. If you're coming from security, you know better than me. Those are the typical way for which we encrypt the hardware, so the data in the router. When we make MACsec, IPsec, OTNsec, whatever, the hardware is done in this way. Then we have the very asymmetric algorithms that are private public key, the PP key, or the digital signature of the software or the firmware of the various aspects. When we speak about the threat, we need to speak about Mr. Shor. Mr. Shor is a mathematician and physician of the MIT that at the end of the 90s of the last century said that, oh, by the way, if a quantum computer that will have enough power will be able to run this algorithm, I will be able to break RSA-based algorithm. The RSA are, again, coming from the security, the RSA are the algorithms that are used for the asymmetric ciphering, so the public-private key, like the Diffie-Hellman, elliptic-called Diffie-Hellman. The RSA is used, for password on your bank account, password certification, something like that. That is what is the major problem. The symmetric cipher, like the AES 256, 512, 1024, those are not under risk at all at the moment. So this is what is creating at the moment the threat. Because, summarizing, so what can do in theory? If I have a public key, I can give to a quantum computer, and the quantum computer is able, theory, applying the Shor algorithm, to find the private key. So they are using for identity, TLS certificate, hardware SUDI, software signing, key exchange. I can capture the data encryption key, so I can decrypt secure data, the malware, I can spoof the endpoint, I break remote attestation. That is the threat that we are speaking about at this moment, and why there is this industry, back and forth. Many people is asking, yes, this is the theory. Mr. Shor was a genius physician that created this wonderful algorithm, but is the threat real? So look at this graph. This is a nice graph that is telling the number of logical qubits versus when a quantum computer with that number of logical qubits is planned to arrive. You have 3. The green is the most optimistic, the orange is probable, the negative is the blue one. When I speak about Shor algorithm with enough power, it has been calculated that I need 4,000 logical qubits to be able to apply the Shor algorithm to whatever stream of data. Today, question, who knows who is the highest number of qubit quantum computer now existing in the world? Sorry? That's a good question, you know, physical. Sorry? Okay, let me, in the West country that we are aware, let's set up. IBM won with 1100 physical qubit. And he made exactly a very good point. We are speaking about physical qubit. There is a difference between physical qubit and logical qubit. Physical qubit are really the qubit built with the matter, with the photons, whatever it is, the real qubit. The logical qubit are qubit without errors. Of course, to apply the Shor algorithm, I need a no error capability. So I need 4,000 of logical qubit. Today we are 1,100 physical qubit. The ratio between logical and physical is various. So in the sense there is a strong dependency on which correction algorithm you are applying. The various quantum correction algorithms are currently still under study. We don't have yet a good one. So could be the ratio also of 100. So it could be that if someone will not come up with a genius application, we are speaking about hundreds of thousands of physical qubit before able to. But you know, there are so many billion and so many researchers that could be that come up, somebody will come up with a wonderful quantum error correction and having a quantum computer sooner than later. And so this is the problem. The problem will be the retroactive attack. Because today, everybody are safe. Nobody can touch me. But unluckily, federal government, finance, various institutions require to maintain data for 10 or 20 years. So I can, at the moment, spill the data, store it. If in 5 years a quantum computer will arrive, I can decrypt it, breaking the cipher. And so this is a major problem for those institutions that has a mandate to maintain full secret for the data for 10, and I heard also people that need 20 years. And this is why there is this big hype in the market, because you know, could be a threat. Maybe quantum computer will arrive in 2040 and I'm safe, but maybe the quantum computer can arrive in 2030. That is a major problem. So this is why the NIST, that is the standard that has to define all the various algorithms, decided to open, still back in more than 10 years ago, open to all the world, hey guys, we need to find a solution for a possible quantum attack. Please invent new algorithm, a mathematical algorithm that will be safe from a quantum computer attack. Initially, it was more than 90. Also, Cisco tried to propose one. And then we will see later, it will be selected few ones. And those algorithms, in theory, from the mathematical point of view, cannot be attacked by the Shor algorithm. So now we will see later on where we are. Then, of course, once you have the new algorithm, you need to provide it to a new certification with FIPS, and then you can provide on the deployment. So this is ballpark, what we are speaking. If people require 20 years, so 2015, we are already in a bad shape. As mentioned, 1100 is where the quantum computer was at the end of 2024. So quantum safe cryptography required the migration from 2025 onwards. Again, if people have attended to yesterday's session from the security team with Craig Hill, so you see all the date that the NSA and the US government defined, that is around 2030, to have everything migrated. So if in the best case a 2030 quantum computer will arrive, at least we are in a good position. Any questions so far? Okay. Now, next step. We have the threat. What are the possible solutions? Oh, please.
Shorter RSA.
Yes.
How that goes is RSA 2048.
Mm-hmm.
Historically, I used smaller, shorter.
Mm-hmm.
Is it how many qubits I need to, let's say, break the well?
So for the 2048, I need 4,000 qubit. RSA 2048, yes. That is mathematical calculation. I'm not the expert of that algorithm, so I can only refer.
Talking about 512, for example, RSA 512.
I think that the minimum one of the qubit is around, the low number I saw is around 2,000 qubit. We are speaking about always logical qubit, so that is really the minimum, maybe 1,800, 1,900, but ballpark we are already there. So then, there are, just last week on the news, there was the Chinese that say that we mixing a D-wave, that is a type of quantum computer that, by the way, is very peculiar, combined with the classic mathematical approach, we were able to break the RSA leveraging on Shor algorithm. I don't know how much is, or maybe they have just started to break something, but we are far at the moment to have the full RSA completely at risk. But that is, if this is came on at the news level, can imagine what this is behind that is not reached the news level. So the level of attention is very high for this problem. But what are the solutions that we'll have? Mainly, there are two directions in the industry. One is what is called the quantum key distribution, quantum key exchange, so-called QKD, and the other is post-quantum cryptography. The first one is the quantum physics created the issue with the quantum computer. The quantum physics has also the capability to provide a solution for against quantum computing. The second one is what I already anticipated, is that, there are new nice algorithms that are mathematically safe, and I'm not able to use a quantum computer to break it. Let's speak about the quantum key distribution. So, quantum key distribution leverage on the property of the physics of the quantum mechanics. There are a lot of spread in Europe, because Europe made a lot of investment at the government level about this technology. There are different implementations that are fully standardized in terms of protocol, not in terms of the implementation, unluckily. What we'll show is the discrete variable direct transmission is the most used. There are those two protocols that are called BB84 and B92, that I will go then later what does it mean, that allow to have a quantum safe communication between two server, two router, two switches. There are other variants that will go later on that are called Entaldo-based discrete variable measurement device. There are continuous variable Gaussian modulation capability, but at the end, QKD is leveraged on the physics, and one key principle of the quantum mechanics is that if you measure something, you destroy the information of that. So that is the secret. And so you can intuitively arrive, if I have a communication, if I tap, I'm measuring it. If I measure it, I destroy the information, and so it is completely useless to tap it. But let's go a little bit deep on how QKD is working. The most common implementation at the moment, even if there are others that are coming up, and the number of startups on QKD is growing and growing, is, for example, I give a BB84 example, so discrete variable, and a typical example is the photon. The photon, you know, is the nice quantum of light that we are using. The photon has many parameters. One is the spin, or the polarization, sorry. The polarization, so if you know the light has two polarization. So I transmit a photon, and we're speaking about, and this is a very important thing, one photon. I'm not speaking a light, one photon at a time. So just to introduce the concept that we are really at the edge of the technology, because we are speaking about one single photon. That one single photon has a polarization. There are optical tools, very common, that are called the polarizer. And then if I have the polarization that are matching the one of the photon cross the polarizer. If I have a polarization that is 90-degree shift, the photon is not passing the polarizer. Basing on this concept, I can build this nice protocol. I start sending randomly photon that will have random polarization, and then I create what is called a basis. So a set of polarization on my polarizer that I said, first I put a vertical, then I put a 90 degrees, then another void 90 degrees, another volt vertical. So I have this basis. I can see how many photons are passing through this polarizer. And I am the transmitter, I am Alice, I'm sending to Bob. Bob received those photons. And said that has no clue about what basis I use. And so that, okay, I will try randomly. At this point, some photon will arrive, some photon will not. And then there is a classical communication. Bob sent, hey, Alice, I've used this basis. Alice, that knows what has shipped, said that, okay, let's see if I have used what basis, what could be the error rate that I have added. There are mathematical calculations from the quantum mechanics physics that the error shall have some level, because the mathematics is telling it the probability of that will be that. If the error is too high, and it is physics, someone said that, why I have so much error? Because it means that somebody tapped my photons, measure it. Quantum physics tell as soon as you touch, you destroy. And at this point, this means that somebody is in the middle. And so, if somebody in the middle means that the communication is not anymore secure, and I raise an alarm. This is the protocol, that is the BB84, that is used, and physically is unattackable. There is no way that you can break it, because it's the physics. So it's like the gravity. You cannot start to flying, because the gravity will take you. That is a physics principle. It is not breakable. That is the wonderful aspect. So I said, great, I have a wonderful solution. Let's adopt it immediately. QKD, you can buy. You can go. There are people also downstairs that are selling you QKD solution. Hey, the devil is in the details. Mainly the details is the physics principle, unbreakable. The theory. The practical implementation is the problem. Remember I said that one photon, you know the probability to create exactly one photon, the probability that to measure exactly that photon, it depends on the technology that you are using. And there is the problem. For example, some implementation already showed weakness to counter detector. You know, maybe I can shoot more light, so I can increase the error rate independently that I'm tapping it. And this is create issue. But besides that, the problem is that there is no interoperability nor standard. The protocol is standard, but the implementation from the various startup, everybody use their own one. ETSI, again, Europe that is betting a lot on this technology, is trying to standardize it, but we are still far. Every startup is doing their own. As I have one single photon, you can imagine how sensible is the transmission to any noise. So at the moment, the strong suggestion that we have is that if you really want to use it, please use on a dark fiber dedicated only to that. So you need to dedicate one fiber for that single photon going right and left, on top of the normal fiber for the communication. One photon, is facing the loss of the fiber like everybody, and so is extremely sensitive to the distance. At the moment, the best case we saw is 100 kilometers of delta, single photon between two distant, best case. There are new studies like what is called the twin field QKD that is not yet commercially, that are trying to double the distance from 100 to 200 kilometers, maybe 250, but again, we are still far from a normal implementation, so because having 250 kilometers of dark fiber is not. Another limitation is only key exchange between two servers. The bank password, the software signing, etc. Not because it is protect only an optical fiber, and an optical fiber system between two servers. For all the rest is not applicable. Other problem that we saw, people does not have many fibers. Optical fiber are not cheap. So people said that, look, I already using the optical fiber for normal transmission of system, maybe one channel, maybe multiple channel with the WDM. Let's use the same fiber for the quantum channel. I don't know if you're aware, but when I speak a fiber, I have an optical spectrum, means that I have different frequencies. And a frequency that is used for the transmission is called the C-band. That is a well-defined region of the optical spectrum. Then maybe somebody is using L-band to extend, but ballpark, we are speaking about this region. While the vast majority of the gray interface are in what is called the O-band, that are 1300 nanometer in terms of frequency. So the idea is that, okay, I use this band for the quantum channel, the O-band, and I use the usual classical channel in the C and L band. I am very far. In theory, should be fine. And luckily, no, it doesn't work like that. Because there are nice physical phenomena where it is called the nonlinear effect. When the light goes over the optical fiber, the photons of the light, the normal photon, interact with the matter, with the glass. And some of them create spurious photon far from the C-band. Far, how much far? Also in O-band. Those are called Rayleigh-Raman scattering. Mainly the effect is that if the photon that has a well frequency impact a glass atom, then it could be possible that the resulting photon could be on a different frequency. Of course, is limited. In a normal application, you don't care, but when you have one photon, if you found another photon at the same frequency, that is the problem. It's noise that is generated. At that point, the only thing you can do, okay, I need to reduce the power of the classic channel in order to reduce this noise at the level that I can, in any case, have the BB84 protocol working. Here is how much I need to reduce the power of the C-band overall power versus if I want to avoid to have two noise. From experiment, we made the experiment, you need to have the full C-band at -4 dBm. Just to give you an example. If I don't have quantum, I shoot my C-band at 20 dBm, 23 dBm. So I need to attenuate more than 20 dB. 20 dB, again, is logarithmic. This means exponential. If I needed to reduce the power, I needed to reduce the other output parameter, like the signal-to-noise ratio, and this means that I needed to sacrifice the capacity. Today, if I don't have quantum, I can reach a 76 terabit on 100 kilometers of distance. I needed to drop down to 4.8 T on a fiber pair if I wanted to use the same fiber for quantum channel. There are solutions, and then we are going here on.
Do I have to,
please.
when I drop that speed, then can I use it just purely and only for key exchange and then transfer data with that key on that higher speed? Or?
No, yeah, that's the goal. Those the channel in the C-band are the data channel. So those are the 4.8 terabit are the data channel, the transmission between two server, to data center, etc., etc. The key rate that is on the quantum channel, that is what define the limitation. And then you can see that more noise you have, lower is the key rate, and so then you need to play with that. So that is the main problem, that I need to have the impact on the data channel. So I pay a fiber that is very expensive. I can use 76 terabit on that fiber, and I can use only 4 or 5. They are secure, but it's a penalty. In fact, the message is not that QKD is the absolute evil. No. We have implementation. Cisco implemented, deployed the system with a QKD vendor, but we wanted to raise the warning that it's not so easy as, oh, I put a couple of servers, who cares? It's easy. No, it's not easy. There are drawbacks. It is a complex technology. And so the goal of this session is just to raise the level of attention on think if you really want a QKD, and could be absolutely a fair approach. Again, we have some customers that are deploying it, but need to be with the eyes and knowing exactly what you are facing when you go there. There are solutions very complex to reduce the noise, is what is called the time bin. The time bin method is I will measure the photon, I will open my photo detector for my single photon only when I expect it will arrive. So I will cut all the noise out of that time. And this is helping a lot to reduce the noise. And in theory, you can extend 200 or 300 kilometers more the distance of the single photon. This is only I would say, a research project. Maybe I heard that there are some companies that are studying to have these available next calendar year, but just to alert that there are a lot of things that are running in the system. But now, I don't have those technology. And maybe I have my data center, my location that I need to be secure that are 400 kilometer distance. What I can do? Today, the only thing you can do is this one. I need to have in the middle, every 100 kilometer, a trusted node, so that you are safe, you are secure, nobody can enter, and you maybe break and reopen and recreate another QKD session every 100 kilometers. Complex is that not many people has a trusted node every 100 kilometers. Maybe Army, some federal agency has it, but many people doesn't. In theory, the perfect solution will be what is called a quantum repeater. At this point, the quantum information can be regenerated, even untrusted, because in any case, the qubit continues to be transported across the line. So as soon as you try to measure it, you will break the QKD, and so it would be fully safe. Unluckily, the quantum repeater doesn't exist. Doesn't exist because it doesn't exist commercially. There are many universities that are studying a lot about this. Again, I remember a huge, huge $1 billion of investment on quantum, and the quantum repeater has the beauty to use the same technology of a quantum memory. The quantum memory is fundamental to have, in many cases, a quantum computer with many qubits, and so the effect is that many $1 billion of investment to reach the goal. How it works, the quantum repeater? Mainly, it is leveraged on this wonderful principle of the quantum physics that is called the teleportation, and is based on the concept of entanglement. The quantum entanglement is an extraordinary and totally not intuitive property of the particle that it is possible to create pair of particles, pair of photon, pair of atoms, whatever, that even if they are 10,000 light years of delta, if I touch one, immediately the other will be impacted. It is, again, totally counterintuitive because everybody knows that nothing can be transferred at higher speed of the light. That is a physical relativity. Einstein, in fact, was totally against the entanglement principle. He said that, no, it is not possible. It is a spooky, how it is called, is a spooky connection between the matter, that there should be something that we don't know. Bohr, on the other side, said that, no, it works, it exists, etc., etc. In 1972 or 73, I don't remember exactly, Bell made an experiment that physically demonstrates the entanglement. So now entanglement is demonstrated, from the physics is fully proved. So even if there are, before it was the quantum mechanics that predict this behavior of the matter, now we also have the tested and is fully certified that entanglement exists. And in fact, we have multiple proof points of that. Once I have the entanglement, so I can create two particles that are entangled, that are what is called EPR pairs. EPR stands for Einstein, Podolsky, Rose. Einstein, so Einstein was part of all of that, even if he was not a believer. All the mathematics and the physics come from him. And so it's possible to create, a sort of 2-qubit. I can transfer the information for those two, because those two are entanglement. What I do to something, I will do to the other. And so somebody can say, wonderful, I can transfer the information immediately without any problem. Unluckily not. The entanglement is not violate another principle of the physics, that is that I cannot transfer information at higher speed of the light. What is the secret? Is that yes, I can do something to this, and this will change. But if I'm not telling what I did to this, the receiver is not able to understand what I did. So I need a classical communication to say that, look, I did this, something to this, and so he can understand. So this classical communication, again, is limited by the speed of light. And so again, we are back again to the normal theory. So I can build those systems, and so I can create a quantum repeater, but unluckily, those are university studies not yet existing. What Cisco has mentioned, why we know all of this, because we spent a lot of time and people to test many of those. We made, in 2019, the first demo with QKD. It was QTech, that was a Netherlands company, to transmit a QKD secure channel between those three cities of Holland at such a distance. We made many tests with QKD company, ID Quantique, Team Quantum, QTI, QBird, and there is a long list that is published on Cisco about the fact that we test and we prove that it works. We were at the moment up to 70 kilometers with a single channel. 100 kilometers can only be done with a dark fiber, so a dedicated fiber with a single channel. And we have many studies to model it, to understand, and also study on the different way of QKD. Cisco strategy is mainly not focused on QKD. Cisco strategy says that if you want to use QKD, I will give you a way to use QKD. But Cisco strategy is try to be more comprehensive in the sense that SQKD is only covering when I have a fiber communication. It's not covering SD-WAN, it's not covering firewall, it's not covering many aspects of the network. We would like to more adhere to the NIST mandate. NIST mandate is use new algorithms that are quantum safe. There is a major advantage of that. All the PPK implementation is done via software. So a software upgrade of what is already existing is enough to guarantee that your network is post-quantum safe. And you can see that this is a major impact to your network. Just maintain the same hardware, implement a software upgrade. Respect the QKD, that is external box. Physically, I need to implement it. So if you can say that there are, at the moment, 3 major solutions. The first one is, I mentioned, I use a QKD, external box. There is, but probably you know about it, this skip protocol that is used to interface between the router switch with the external server in case QKD in order to obtain the secure key that then I use to encrypt my data. By the way, the same protocol can be used what is called an SKS server, so a server where I put externally the logic to create those post-quantum secure key and then share with the router. And finally, that is our longer-term goal, that is I implement directly on the box the PQC algorithm in order to be fully safe, IPv2, etc., that will allow to be fully safe and fully compliant for FIPS. Of course, the 3 has a different timeline in the sense that those 2 are already available because they are mainly based on the skip and implementation of software on the SKS. This one has a roadmap that is evolving because unluckily it's not that it is one single software load. There are the TLS, there are the IPv2, there are all the different library of that impact the security communication and the certification of our solution, and this is taking time. I think that between mid of 2025 and end of 2026, we were able to cover all our product in order to be fully PQC compliant from the NIST point of view. Then, of course, you need to take into account all the months that you have to spend for the FIPS certification, but the important is to arrive. So this is mainly how the SKS service is, is an example of QuantumSafe MaxSec, where I can pre-share the key. That is another approach. I can manually pre-share the key that is quantum safe. So that is easy, even if complex to do manually. There is the SKS that is, I would say, a very solid solution. It is a software-based. I need an external server where I run the application that will create the quantum safe key. This is mainly the key protocol, so the secure key integration protocol that is qualified on IOSXE, IOSXR as all of those skip already fully available, fully qualified. So this is the one that can be used easily with the QKD. And I mentioned is already shipping and fully available on mainly all our products. So this is why we have already deployed system that has worked with the QKD because they are leveraged on the skip. And by the way, the skip protocol, even if it is not standard, the skip protocol is a Cisco proprietary at the moment. So that it's very easy to convince the QKD startup to adopt it. Besides that, it's not complex. The standard version is the ETSI, but if you compare the ETSI with the skip, the delta probably are 5 lines of codes. And in fact, what Cisco is doing is already certifying a standardized skip inside the ETF. There is an RFC draft out. And so also that problem, but again, we saw that are zero problem. The QKD startup are so eager to sell their solution that implementing the skip on their box is the last of the problem. So the post-quantum algorithm status, as I mentioned, so when I need the PQC, I need to implement those nice post-quantum algorithms. Everything started in, as mentioned, 10 years ago, better February 2016, that he said that, okay, I want a new PQC algorithm, 92 at the end, arrive at the end in 2023. There was a subset of protocol that are called, one is the so famous Crystal Kyber, public key for the public key encryption, the Crystal Dilithium, the Falcon, and the Sphinx for the digital signature. At that time, we have the BIKE, the classic McElise, the HQC and the CK for the public key encryption. Then there was the final standardization. The final standardization arrived with only the green square. At the end, in 2025, there was another add that was the AQC for these and the Falcon. So at the end, we have a full set of fully certified and qualified algorithm. Sometimes people is concerning is that, no, Maurizio, I want to be fully sure QKD is guaranteed by the physics. Those algorithms, who tells you that another genius come up with a short algorithm version 2 that is able to break those algorithms? The question is fair, but there is an aspect that we need to take into consideration. The level of complexity to solve the new mathematical problem that has been implemented, for example, in Crystal Kyber, is so complex that if you are able to find a quantum computer that is able to break this, the same quantum computer will be also able to break the AES 1024. So that problem, you don't have the problem of the key exchange. You have a problem that also the hardware itself with the symmetric key will be breakable. And so you say that if that is a problem, for sure it is a problem, but the QKD will not solve because you don't care, you break the data, and so that is not that will be the major problem for the industry. But in any case, that is a question that is absolutely fair, and I think that there are universities that are trying to understand if there could be new quantum algorithm that can break those kind of problems. But again, that is why the universities are there to study those problems. So far, we are safe. Okay, so we are at the end portion of the session. I would like to remind about QKD versus PQC. QKD has require dedicated hardware, nice box that are, by the way, very expensive. One photon, so I needed to be extremely precise on that. Due to that, I need a noiseless optical quantum channel. We are limited to 100 kilometers in terms of dark fiber, less if I want to use the same channel for also the classic WDM system. So far, no standard, no interoperability. Address only key exchange, not the authentication of the rest. And there are some weaknesses that has been analyzed to counter the attack. Of course, The weaknesses are like the usual vulnerability study. If you find the weaknesses, you're changing the implementation, the vulnerability goes away. So again, the QKD is a new technology. I'm expecting that it will mature and probably most of them will be solved. But that in any case, my message is, let's highlight that implementing a QKD network is not so easy, doable, but let's think about it. Of course, our solution will be, let's focus on the PQC. We don't need a dedicated hardware. It's a software upgrade of the existing hardware that has been already implemented. And by the way, you need also the digital signature that is not minimally managed by QKD is a problem that I need to fix. So in any case, the PQC will be needed for at least those portions. Then there are people that are trying to understand, I can increase furtherly the security of my network putting them both. Absolutely fair. You can use PQC and then on top of it, putting a QKD for additional security. In some cases, probably is too much, but again, absolutely free to offer that kind of services. So, final walk-away message for the security is that quantum computer threat is real. It may break the RSA by 2030 in optimistic way, even if, again, with all the $1 billion spent on quantum computer, maybe it's not so optimistic. QKD is absolutely a solution that is valid, can protect the data, can enable key security, but as mentioned, I need dedicated hardware. The key generation rate drops exponentially with the distance, and beyond 100 kilometers, at the moment, we don't have a solution. Post-quantum security, as mentioned, is a way that Cisco suggested. It's a software upgrade. Of course, we needed to wait the roadmap. If today you have absolutely need to have that, an ICE SKS server can make the job. That are exactly, and the skip protocol and RFC 8784, that is the pressure keyed, is what is fully available now for such application. So that's it. You can complete, please complete the session evaluation, and that's it. You have any question about this topic? Is anyone thinking to implement the QKD? Oh, great. There are companies I saw also downstairs that are selling solution from this pure software point of view to manage a QKD network like yours. Maybe you can check. Not Cisco, so I'm just... okay, that is better. No, that is what their company are doing. That's what they mentioned. There are people that are working with the API, with the box. Oh, okay, understood. Okay, yeah. It's a new technology as mentioned. So unluckily, those are the pain that we need to suffer when that kind. But again, you are not alone in that condition. So I heard other people that has exactly the same problem. Those are all physics. You can speak about quantum physics, wonderful. But when you arrive with, give me a netconf Young model. Netconf model, what it is? I can imagine.
But they are the most stable, especially on the optical side. When we had issues,
they have a long experience, by the way, yes.
They are doing detectors.
Yeah.
Long way before.
Yes. Oh, thanks for the feedback. No, that's absolutely not. That is a very good feedback. Other question? Good. Thanks a lot for joining this session.